Hello students. So in this session we are going to discuss some of the important points in this chapter. Although this chapter is a small chapter, but still there are many important concepts which are uh, useful in solving the problems. So next thing that we are going to discuss in this chapter is about uh, the rods or the wires in series. Suppose there is a rod or wire is hanging like this way. For example, this is one wire, and then there is another wire, and at the end we have a load or some block M. Okay. So what happens in this case? You can consider this as an equivalent system of spring. Right? You can consider this as a system of spring connected like this. We can convert this into this situation. Now let's say this is K1, this is K2. So its length is, let's say, L1, its Young's modulus is Y1. Its length is L2, its Young's modulus is Y2. Areas of cross sections are same, common cross section areas, right? So just like spring connections in series, what happens is that the elongations, let's say elongation is x1 here, x2 here, those elongations are different, but total elongation x can be written as x1 plus x2. We want to find the equivalent rod, which is the same concept as equivalent spring. So this x is nothing but the force F by K, right? F by K, F by K1, F by K2, F by K equivalent. Remember here that the tensile force remains same. So this force which is acting, internal forces remains same. So we can treat it like this, and once you remove it, 1 by K equivalent. Now K, I told that K is AY by L. We can use this. So here you can write area is also same. If you want, you can write it Y by, you have to take reverse of this, right? Reverse of this, 1 by K. So it will become L by AY, correct? And L equivalent, A same, Y equivalent, L1 by AY1 plus L2 by AY. And if you want to keep the equivalent length same as total length, so L equivalent can be taken as L1 L2 by Young modulus, L1 by Y1 plus L2 by Y. This equation we can use, right? In case if they are in parallel, wires are in parallel, like for example two rods, one rod, another rod. This time the length of the rods are same, and they are put in some ceiling, and here a block is connected, or there may be some like a common platform where block is hanging like this, that you can see. So definitely here the elongations that are going to happen, that elongations will be same in each of the rod. Each of the rod behaves like a spring here, right? This way it is connected. So let's say this is K1, K2. In the same way here Areas can be different now. Length modulus are anyway different. But length has to be same. Same length L and same length L here. Right? So in this case, the total force acting, this is equal to F1 plus F2. So the total force is F1 plus F2. Total force here is mg. Right? mg, that is equal to F1. But we want to write in terms of equivalent. So F you have to write as K equivalent into X. This is K1 into X plus K2 into X. So here in parallel, the springs gets equivalent gets added. Now when you are writing K AY by L, A equivalent, Y equivalent, length is going to be common. So A1 Y1 by L, A2 Y2 by L. Right? So what equation we will get from here? A equivalent, Y equivalent, A1 Y1, A2 Y. This can be used, right, for parallel combination of wires. Right? Okay, then next. Sometimes there can be a rod which has different cross sections. For example, like this, then like this, and then some different cross sections like this. Okay, so let's say this cross section is A1, this cross section is A2, this cross section is A3. Different cross sections are there, and you have applied some force, some load or some force is applied. Some elongation will happen, and let's say its length is L1, this length is L2, this length is L3. Its Young's modulus is Y1, Y2, Y3. So here again you have to take that some deformation will happen. This total deformation or total X equivalent, if you say, then because they are in series, right? So total elongation will be elongation 1 plus elongation 2 plus elongation 3. Like that you can write. Now elongation, total elongation, if you want to write, that elongation will be first. You have to calculate. Separately you can calculate. Okay, let me put here itself. So force by K, K1, force by K2. Here force is the same, force by K3. Again K is nothing but AY by L. So A1 Y1 by L1. Same manner you can write this, A2 Y2 L2. Right? So this way total elongation, X equivalent means net elongation, we can calculate. Okay, right. Then self elongation is important topic. What is self elongation? Self elongation. Suppose, for example, that there is a cylindrical rod which is hanging. Because of its own weight, let's say its mass is m and length is l. Because of its own mass, it is going to hang. So if you consider distance x from this end, so at this point, this weight which we can see here, this block or the lower portion will be stretching, right? So you can take a very thin cross section like this, dx, let us say, and this dx element is getting stretched because of tension. This side tension. That tension is weight below that. So this length will be L minus x. So this tension will be equal to mass per unit length into this length, right? This is the total mass below this into G. That's the tension. So this is creating a small elongation here. This is a small dy I have taken, dx I have taken, or you may also write as dy, but let's say okay. So small elongation I'm writing as dl here. dl is representing here as small elongation. Is force F or tension here, F into length equal by A into Young's modulus. Now we can integrate it to get the total elongation required. That is known as self-elongation. Okay, so if you do that, let us bring the things out. So mg by Lay will come out because tension will put mg by Lay, and we have to integrate L minus x dx. And x is going from here, x is going from 0 to L. So mg Lay L integrate L into x minus x is x squared by 2, 0 to L. Substitute. So mg L square, 2 factor will come, 2Lay. That is what it is. In terms of density also you can write, because area into length is volume. Area into length is volume. So mass by volume can be written as density into G L square. Right. Here LL can be also cancelled, and you can write this as mg L by 2Ay. But if I am going to write this in terms of linear mass density for the rod, but linear we should not take because area we are considering here, it's like a cylinder. So area into length become volume, mass by volume become density, density G L square by 2 Young's modulus. Right, so self elongation can be calculated. Either you write this or this, anything is okay. Right, in terms of densities or in terms of mass. Self elongation is important to consider. Now there is another approach, shortcut approach to solve it, self elongation. That shortcut is, suppose the rod is given here, you consider the center of mass. Center of mass here. So now what will happen? This weight is acting at the center of mass. We consider the length as half only, and you can directly calculate elongation Fl by F is total weight, and length you take L by 2, Fl by A by. Directly you can take mg L by 2A. This type of shortcut can work only for a uniform rod. For non-uniform rod this will not work, right? For example, if it is a different shape, or if it is changing, the density is not constant, not a uniform. But for simple things you can do it. Okay, let's move next. Sometimes questions are given that if a rod is rotating about that point, then how the total elongation or tension will be there. So in such case, first of all, let's understand this, that if there is a rod and if you start applying a force here, then what will happen? Let's say L is the length, M is the mass. Will there be any elongation in this case or not? The full body is moving here. So will there be any elongation? Body seems to move as a whole, definitely, but any cross section you take, there will be an internal force developed. Because of this, there will be elongation. Yes, we can think about it. So, if you consider at any point, let's say here, the distance of x from this end. So, at this end, what will be the tension force? You draw the free body diagram. Tension is like internal force acting like this, and on this tension will be like this, isn't it? So you know the acceleration. First of all, acceleration is force by mass. Once you know the acceleration, this tension is like the net force, which is mass of this portion, which has length L minus x. This is x. So mass per unit length into the length L minus x. This is the mass into acceleration, which is F by capital. Okay. This is according to Newton's law. Tension is the only force acting on this L minus x length, right? So this is the mass into acceleration. Now here mass get cancelled, F 1 minus x by L. You can see this is how tension is varying along the length of the rod. X0 means tension, and maximum tension is acting only at x equal to 0. As you go, x is equal to L tension. So there is a tension developed which is the internal force, and this tension is variable. Linearly it is varying along the length. My question is, due to this tension, is there any elongation? Yes, definitely it is, because this tension is pulling each part into different ways. So you need to take a small element dx, and you have to write this small elongation dl, and from the free end means from this end where you are applying the force, from that end let us take the distance as x, right? So this small elongation f means tension there, fl by length is dx, fl by a into Young's modulus. So tension is nothing but f1 minus x by n dx, and this is e. Now let us do the integration, total integration, integration of dn. F by ay comes out, integration of 1 becomes x, x becomes x squared by 2, right? Then this is going from 0 to f. Let us calculate that. F by ay, this is L minus L squared by 2n, and other things will be 0, right? So f L squared by 2a1, it is like f L by 2a. It is same as like mg force is acting, so mgl by 2a, like previously we have seen that exactly in the same manner. But we know the tension is changing around length, and because of that it will happen. Okay. Next thing, what about if a rod is rotating? So let us consider that there is a rod which is under rotation about the midpoint. Okay, total length is L, total mass is M. Now how does tension is varying? So you need to approach the same way. Suppose you take a point here, okay, at a distance of x from here. Let's consider it is going with the angular velocity omega. So because of that, you can consider this portion of this rod. So this is definitely L by 2, because here this is L by 2. It's L by 2 minus x, right? So this portion, if you see, the tension will be pulling it. That tension will be mass of this part. Let's say that mass is smaller. M omega square into radius. Radius means its center of mass. You have to see. This center of mass is at this distance, radius. M omega square r. That r we can calculate, because already this x is there, plus L by 2 minus x divided by 2 we have to do, because half of this length we have to take, right? So from here this will become x plus L by 2, right? Or L by 2 plus x, L by 2 plus x by 2, right? This is our, so let us do that. Mass, how much mass will be? Mass is mass per unit length, by mass per unit length into the length of this portion. This portion length is L by 2 minus 6, total mass of this. Now let us substitute it here. Tension you can calculate. Capital M by L. L means this total length only, right? Into L by 2 minus x. Omega square, this radius is L by 2 plus x by 2. So M omega square by L you write into 2. And this can be written as L square by 4 minus x square. So this is how tension is changing, right? If you take when x equal to 0, tension is maximum, right? So tension equal to maximum at x equal to 0, and that maximum tension we can calculate M omega square, L will get cancelled by 8, right? Okay, so we can calculate tension here also. Because of that tension there will be elongation, so we can integrate that and calculate total elongation. So total elongation, when you are calculating the same way, right, we are taking a small portion dx at a distance of x. So total elongation, integration of this, it is tension acting FL by A1. Here tension is given by this, so tension is M omega square by 2, M omega square by 2. AY comes out L square by 4 minus x square. L square by 4 minus x square dx, this integration. So M omega square by 12A1 L square by 4 into x minus x cubed by 3, and here length can go from where to where. While doing the total elongation, I think we have to consider both sides. That means you can go from minus L by 2 to plus L by 2. Let's check that total elongation you can calculate. M omega square to L put the upper limit square for x is L by 2 minus L by 2 whole square, so L cubed by 8 into 324 minus L square by 4. This becomes minus L by 2 minus 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 will become plus L3 by 24. Okay, so let's open this. So m omega squared by 2 L Here these terms will get added. Both the terms I think will get added. First find out what it is. So 2 times I think it will become. Right? Isn't it? So 2 times of this will come. How much this is? L cube by 8 minus L cube by 24. So these two will anyway get cancelled here. So m omega squared by L1. This become 24, let us say 3 minus 1 2. So m omega squared L cube, 1 L will get cancelled, L square, this is 12 A1. Okay, that's the elongation due to rotation. So m omega squared L squared by 12 A1. We should know. In the same approach, we can solve questions, right? Then what else? So we are done with this. Then different type of questions coming in the same manner. One more model question you can take. For example, if they give that rod, let us say if they give rod like this, and they say that here some force is acting, let us say 60 kilonewton, here some force is 50 kilonewton, and some cross section they show here 20 kilonewton, and some cross section here they show 10 kilonewton, and lengths are given, let us say 1.5 meters first length, second length is 1 meter, third length is 2 meters. Okay, and their Young's modulus are given. Young's modulus y is given in the question. Each of the means it's the same rod, you can see. So what will be the total area is also given. Area is also given. Total elongation they ask. Total elongation. That's the question. To solve this type of question, what you are going to do is, you can start from one end and let us apply the forces. These forces given are external forces. We have to balance by internal forces. Let us take this. Let's write this as the first part, this is second part, this is third part. Let's take the first part. On this first part, the forces which are acting here, this force is 60 kilonewton, right? If this side is 60 kilonewton, you need to consider this side force, internal force that must act is also 60 kilonewton. But here you are applying a force of 10 kilonewton this side, isn't it? You are applying 10 kilonewton. Resultant this side must be 60. How much this side? This resultant should be 60. Okay, resultant should be 60 this side. But what is that? Resultant should be 60. This must be 70 kilonewton. Then only 70 minus 10, right? So 60 we have balanced it. Now let us go. So internal forces here is 70. Okay, this is the internal force acting at this place. Now go for the second part. Same 70 kilonewton must act in this way because the internal forces act in this manner. Then what else here? Already you have considered this force 10 kilonewton. You don't have to consider again 10 kilonewton at this surface. Then you have to see other side. Other side resultant also must be 70 kilonewton. But what they have given here is 20 kilonewton this way. That means you have to add the internal force of same. You have to add the internal force of 50 kilonewton, right? Now go to the third body. On the third body, we have to add 50 kilometer internal force like this way. Okay. Then this side, how much it is? Just check. This side is 50 already acting, right? It is balanced. It gets balanced in this manner. So forces for such type of complex system, we have to do it like this. Once you know these forces, then you can calculate elongation for each of these, first part, second part, third part. Then total elongation can be added. So total elongation is elongation in the first plus elongation in second plus elongation in third. Each elongation is force F1 Fl by A1. The y's are same here, so no need to worry, y and areas are same. Force and length are changing. So force here, for example, for first force is F1 is 60 here, F1 is 60 kilonewton, F2 here is 70 kilonewton, and F3 here is 50 kilonewton. So we can use this and we can do the calculations for this type of problems. Okay, then next one thing is about torsion, which may not be in the syllabus, but let's know about it. After that, I think bending of beam, and then we will be completing this. Okay, let's write this. For shaft, okay, rotation or twisting of shaft, twisting of a shaft. Suppose that there is a shaft like this. Shaft means it's a solid cylinder, okay. Shaft is solid cylinder. Solid cylinder. So in this solid cylinder, let's take that this is the axis, and you assume that this side it is fixed somewhere. This side is fixed in a wall. Now here you can take 2 points. Let's take this point is A, and this point is point B, and you are trying to rotate it. So because if you rotate, what will happen? This point B will go like this. So initially the line is AB, which is horizontal. Because of twisting, what will happen? This line will become like this. So there will be some angle rotated here, phi. Okay, and because of that, this point B is going over the circumference, so B is rotating some angle, right? B is going to rotate some angle. The angle rotated by B is theta. On this circle it is rotating, right? So what is the relationship between them? That we need to understand. And this is like an arc length here. B dash is like a circular arc. So definitely this theta is equal to, and suppose the radius of this is r, this is r. So this theta is equal to b dash, that arc length divided by radius, and this is the length here. So this phi angle in radian, that is also like b dash arc length divided by this radius. So you can take the ratios, and this angle phi is like the angle of twist. Phi is angle of twist. and theta is the shear angle of shear. So here we can get the relationship phi by theta. If you do, you will get R by L. Okay. So there is a relationship between them. We can calculate angle of twist phi is equal to R theta by L. Okay. This equation sometimes can be used for calculations. And if they ask how much work is done in rotating, so work done is half into the torque into the theta. This tau is nothing but it is the torque which is applied. Torque. And this angle theta is the angle through which it is rotating. Okay, or rotation angle or the angle of shear only we should consider. Because to be able to do that like this, you are applying some torque. Without torque, how can you make this angle? So you are applying some torque here basically, isn't it? So that torque, assuming that's a constant torque, or if not constant, then we are taking like average values. Otherwise integration you have to do, isn't it? So half torque, I think this is nothing but the average work done which can be taken, right? Average work done. One end is free, another end is fixed. Okay. Then what is torsional equation? That's the important thing. Torsional equation. Torsional equation of a shaft. Torsional equation of a shaft. What is a shaft? Shaft is nothing but a cylindrical, element which you can consider it like this. Okay, and let us say one end of this cylindrical element is fixed in some valve, rigid valve, and let us consider a horizontal line here. This horizontal line is right now straight, right? Let us consider this as the axis of the cylinder. So if you apply a torque, let us say you are going to apply a torque, right? So point on the valve which is connected here, this point is not going to change. Let's say this is AB. This line is right now like this. So after you are applying a torque, there will be a twisting effect and this point B will come here as B dash. So there is a twist happen. Let's say phi is the angle of twist. Angle of twist. Let's say the length of this shaft is L and the radius of this shaft is R. Okay. Now, first of all, we are not going into derivation of the torsional equation, which is beyond the scope of our JEE syllabus. But let us write the torsional equation. So the torque which you are applying is the torque tau. Of course, this is external torque. So an internal torque will be set up in this, right, which will try to bring it back to its original state. That is the internal torque. This internal torque is due to the intermolecular forces, right? So in general, we can write this torque. This torque can be either internal or external. So torque by J. What is J? I will explain. That is called polar moment of inertia. Then that is equal to the shear stress. This is the maximum shear stress, of course. This shear stress is the maximum shear stress. Okay, divided by radius is equal to G phi by L. Here G is the shear modulus of rigidity. Shear modulus of rigidity. And L is the length of the shaft, as you can clearly see. What is confusing terms that I am explaining here? Like what is J here? J is called polar moment of inertia. Polar moment of inertia. What is polar moment of inertia? That you don't have to right now go into detail, but you can note that this polar moment of inertia for circular cross section is pi by 2 into r power 4. This is for circular cross section. Circular cross section. Right? G is the shear modulus phi is angular twist. R is radius, L is length. Shear stress is the maximum shear stress. Okay, and tau is of course the torque here. So this tau is nothing but the torque, which is, you can say, internal torque. Internal torque. So this is the restoring torque, you can say, restoring torque, which is same in magnitude as the external torque which you have applied. Okay, this equation can be used to calculate many things, not just only about the torque which is acting, but let's understand some applications of this. So for example, from here if you see torque can be written as Gj by L into phi. So you can see that the torque which you are applying is proportional to the angle of twist phi, and this is acting like a torsional constant. Torsional constant. Anyway, we will not go into more detail about that, but if you substitute these values here, what you will get? This torque G is shear modulus of rigidity, J pi by 2 r power 4 L into phi. Right? So you will be able to calculate the maximum torque which you have to apply, or this is the torque within the elastic limits, just like there is Hooke's law. Right? Same way. So this torque which is acting is proportional to the angle of twist, and this factor that is called torsional constant. Right? Okay. Another thing that we can note here is shear stress. We can also get relationship between torque and shear stress from this, because this equation involves three things, right? This equation which is a very important equation, particularly from engineering point of view, right? So here you can also say torque relationship with shear stress, right? So this torque is related with the shear stress, maximum shear stress divided by R into that polar moment of inertia. You can multiply and you can get this equation, right? If you know the maximum shear stress, you can substitute and you can find out the maximum torque that is applied at the surface. Remember this torque which is applied at the outermost surface. This is the torque applied at the outermost surface of the shaft, right? So using that we will be able to calculate this. So this is like the maximum torque, you can say. This is like maximum within the limit, otherwise it may break down. If torque applied is more than this value, it will break down the whole shaft, or this cylindrical element will break down, right? So this is what we need to do. Next thing that we can understand more about detail is about the bending of the beam, right? So if you consider the bending of beam, in NCERT you will see that they have covered some part of it, that only with just formula, but little bit I will describe here, which is not found in the textbooks, but which is important for you to understand. Okay, so first of all, what is beam? And you should also know about what is column. So beams in general, beams or columns, they are they are part of constructional elements. They are elements used in the construction of building structures. And how does it look like? So beam is known as the horizontal part or horizontal element, and columns are like the vertical element. If you are in the first year of your engineering, mostly this is a course called Strength of Materials, where you will be covering this in your engineering institutes, particularly in civil engineering, mechanical engineering, even electronics and others engineering. They cover this course, okay, in the first year or second semesters. Okay, so anyway, let us understand here. Beam means just a rough idea that we should have, like some kind of vertical element or structures, and in the buildings we also have like the vertical structures. So these vertical structures are called columns, and the horizontal elements are called beams. Now the beam, there is an important thing about the deflection. So as we have discussed that there are deflections or elongations due to self weight. So same manner consider a beam. Now beam are of different types. Here in NCERT, if you see, there are two types of beams are discussed. One is the simply supported beam. If you consider beam like this, where one end is fixed in the wall, and second case where the beam is like this, and they are simply supported like this. Okay, they are horizontal elements. So the first part is called cantilever beam, and this is called simply supported beam. So here we are bothered about finding the deflection. For example, if you see like this type of cross section beam, so due to self weight, it will happen like this. Not exactly this one. Here it will be bending like this way. Definitely. Why it will bending like this? Because there are loads due to its own weight. Here this will be like that, the previous shape which I was trying. And this will be bending in this manner, okay, due to self weight. So we want to find out the deflections happening, and the maximum deflection is like here the end. The maximum deflection, why? Maximum deflection. Here the maximum deflection happens at the midpoint, right? So we are interested in these calculations, and we should know the formula for this. Okay. So let us write about this deflection formula. So in general, the deflection formula for the cantilever beam, we can write y is equal to the weight. So it will be having some weight, right, or some kind of load. So what do we consider here? Its own weight or some external load? So I think here we need to consider the beam as massless. Let us consider beam has no mass, right? So massless ideal case you take. So you are going to apply some force at the end. Let's say you are applying a load at the end. You are applying some load. You can take some force. You can take W. W is the weight in Newton. Weight is of course a force. Here the weight is applied at the center, so that weight W we are taking. Okay, in both cases. So how do you calculate this y? So y will depend on simple formula is there, that W L cube by, for this cantilever beam, 3 y is Young's modulus, and I is a term called area moment of inertia that I will explain. And here this y deflection, we are talking about the maximum deflection. Okay, we are talking about only the maximum deflection. So the maximum deflection here will be W L cube by 48 y into I. Now y is here Young's modulus. Young's modulus. And what is I here? That I we should note. This I is called area moment of inertia. Area moment of inertia. And this I is given for different cross section we can calculate. So b dq by 12. This formula is for like a rectangular cross section. Rectangular cross section. Rectangular cross section area of beam. For example, suppose the cross section area is like this. So this is B and this is D. Similarly, this I can be written as pi r power 4 by 4. This is for circular cross section. Circular cross section. Circular cross section like this, whose radius is r. Okay. Now this I has a major impact here. Consider the length same, Young's modulus same, so I is going to have a major impact here, because in both the cases, of course, here other numbers like 3 is there, here 48 is there. We don't have to bother right now that how they are going to derive it. We don't have to really go into this right now. So what we need to understand here is y max is inversely proportional to I. Y max, here we can note this fact that y max is inversely proportional to I. And let us consider a rectangular cross section. Rectangular cross section. So BDQ is going to be here in the denominator, right? BDQ. So if you change the B and D accordingly, right? It has a major impact here. So B dq will be, for example, suppose if you take D large, then y max will, because D has a power of 3 in the denominator. That has a major impact. So if you increase D, then y will decrease, deflection will decrease. And if you decrease D, then that means if you keep, like for example, if you keep the beam cross section like this, and if you take the beam cross section like this, they have got major impact. For example, in this case D is large, this D is large here, and in this case D is small. D is small, right? So in this particular case where D is large, y maximum deflection, y maximum is going to be less, right? But in this case y maximum is going to be large, isn't it? Yes, of course the other factor is B is also going to matter, because B has also impact here, isn't it? But if you can, let us say B is constant. Suppose for example here I keep the B as constant, then maybe we can understand this better, because this is B. Let's keep B as the same, right? But D I have decreased like this. So B is same, but D is smaller now. So definitely we can say that y max is going to increase, right? Because D becomes smaller, B is same, so maximum deflection will increase. So this is how the design of the cross section area of the beam is going to affect the maximum deflection. So basically, in one sense, you can say that the area of cross section you are going to increase. If you increase the area of cross section, increasing area of cross section area of beam, increasing cross section area of beam decreases the deflection, decreases the maximum deflection, or in general deflection of beam, right? So it is safer. So what about if we increase the cross section area? Then we will have lesser, but if you have a smaller cross section area, then this will be larger. So we should try to increase the cross section area, but at the same time we should make sure that design should be efficient. So for that purpose we are using I cross section area. Cross section area is of I-shaped. So I-shaped beams have this advantage. I-shaped beams suffer lesser deflection, and that is why they are used for engineering applications, right? This is one of the things that they can ask in the questions. Besides this, I think we are done with this chapter. These are some of the extra topics that we have discussed, right? So thank you for your attention, and then we will be moving with more about the problems of this chapter in the next session, right?